the first type of radiation that we'll talk about is alpha decay. And it's called alpha decay because it emits what we call an alpha particle. Alpha particle is simply a helium nucleus. It's 2 protons, 2 neutrons. So it has an atomic number of 2. It has an atomic mass of 4. It's actually the heaviest of our 3 types of radiation that can be emitted. It's charged because it's just the nucleus. It's just the 2 protons, 2 neutrons. There are no electrons associated with alpha decay. It emits that helium nucleus, so it has a charge of +2. It also is it's relatively massive because it's the 4 particles. So they move fairly slowly, but they're pretty strong ionizers because of that +2 charge. And because they're moving so slowly and they don't have a whole lot of energy, relatively speaking, it can be stopped pretty easily by a piece of paper. So let's look at an example of alpha decay. We start with our parent nucleus, which in this case is uranium-235, right here. So our unstable isotope is uranium-235. In order to become more stable, it releases or gives off an alpha particle. So we see, here's our symbol for an alpha particle, the little alpha sign. And again, though, remember back to our notation. We could just as easily write it as this, He2, Here, instead of the He, they use the alpha, the lowercase a. But again, notice the 2 and notice the 4, which are our atomic number and our atomic mass here. So we have 2 protons, 4 nucleons, which means we then have 2 neutrons. Again, it's our helium nucleus. Then we have our daughter nucleus is thorium-231. Now notice how we're writing or how we're distinguishing these nuclei. Uranium-235. The 235 that you're seeing there is the atomic mass of that particular isotope. And so if we were to write it out, uranium, there's our atomic symbol, our chemical symbol. Uranium has an atomic number of 92. It has, therefore, 92 protons. Its mass number, or the mass number of this particular isotope, is 235. Hey, uranium-235. Now the daughter nucleus, remember that we're losing an alpha particle, just 2 protons and 2 neutrons. So thorium, which is TH, it's losing 2 protons, so its atomic number is going to drop by 2. So thorium has an atomic number of 90, but its atomic mass is dropping by 4, so that's 231. So that's where the thorium-231 comes from. Next we have beta decay. And beta decay involves a situation in which a nucleus emits a beta particle. A beta particle is what we call an electron. So electrons and beta particles, same thing. It also releases what we call an antineutrino. Now, the antineutrino is actually the antimatter particle to the neutrino, and it's a particle that at first was only theorized, and it was theorized to support the conservation of momentum and conservation of energy in a beta decay reaction. And because if you just look at the decay and we only have the electron and we have the daughter nucleus, then what was discovered was that momentum and energy conservation principles were not followed. And so it was theorized that there had to be some other thing being generated, and it wasn't until many years later that the antineutrino was actually detected for the first time. And so in the process of beta decay, a neutron actually changes to a proton and an electron is emitted. And within this, the neutron that's in the nucleus actually turns into a proton. And so the number of particles in the nucleus, the number of nucleons stays the same, but the number of protons and the number of neutrons changes. And it's important to realize that in this reaction, we're not kicking an electron out of the electron cloud. So it's not losing an electron, it's not becoming charged. As part of the decay process, as part of that neutron turning into a proton, you're actually creating an electron. And that creation of the electron is, again, to conserve mass, energy, and momentum. And so there's actually an extra electron involved or related to the daughter nucleus than there was with the parent nucleus. Now these beta particles, these electrons, obviously they're not as charged because it's only -1 instead of 2, and they're lighter because there's an electron instead of having 4 nucleons. They travel a little faster, they can travel through a little bit more, they get through metal and plastic, they can get through paper, but they get stopped by things like metals, plastic sheets, so kind of thicker material. Looking at an example of beta decay, we start with a parent nucleus of potassium-40. Potassium, which chemical symbol K, has an atomic number of 19 protons, and the atomic mass here then is 40, which tells us that it has 21 neutrons. And so this is an unstable nucleus. So to make it more stable, one of those neutrons, one of those 21 neutrons, is actually going to become a proton. And so the daughter nucleus is calcium-40. And so calcium, which has an atomic number of 20, okay, so there, see where we go from, and here's something important to notice. So we're going from 19 down here, we have 19 protons in the potassium, we have 20 protons in the calcium. But what's not changing is the atomic mass. The atomic mass of that new calcium nuclei is still 40, because all we're doing is we're switching one of the nucleons. We're not adding or subtracting nucleons. One is simply being converted from a neutron into a proton, and as part of that, we're releasing a beta particle, which is this electron here, and an antineutrino. Okay? And so you're looking at your antineutrino, you see it has 0 nucleons, basically. It has 0 charge, 0 mass, 0 nucleons. So it doesn't do much. Then the third type of natural radioactive decay is gamma decay. And in gamma decay, we're giving off gamma radiation, which is that little lowercase upsilon there that you see. And gamma radiation is a type of electromagnetic radiation. It has very, very high energy. In this type of radiation, there aren't any particles, there's only that energy being released. And so this actually occurs when you have an excited nucleus. And just like electrons have energy levels, nuclei can have energy levels as well. The difference, though, is that the energy levels in nuclei involve much greater amounts of energy than the energy levels or the energy changes when we're talking about electrons and their orbitals. And so some type of collision, there are a variety of ways, gets that nucleus into an excited state. Well, it doesn't want to stay in that excited state. So similar to how our electrons go to a higher energy level, drop down and release energy, so also our nuclei can get in a higher energy level. When they drop back down, they release that energy in the form of electromagnetic radiation. It's so much energy that it's gamma radiation, and it releases a photon. It releases that photon of energy. So let's kind of sum up some of the properties of our different types of radiation. So the first is an alpha particle. It's the largest of our 3 types of radiation. Helium nucleus, 2 protons, 2 neutrons, has a charge of +2. So compared to the other 2, high mass but a slow speed. Has a very strong ionizing effect. Now, when we say ionizing, that means that it has the ability to take electrons, and because it has that +2 charge, it's a pretty strong ionizer. It's very easily going to pull electrons off of something else. It's going to give something else a charge in order to neutralize itself, but it doesn't penetrate very well. So, strong ionizer, but weak in the penetration area because of its slow movement. It doesn't have a lot of energy. And then kind of another property that we can use to identify our types of radiation are its effects, or the effects of magnetic and electrical fields. Because an alpha particle is a moving charged particle, it's going to be influenced by magnetic and electrical fields, and so it can be deflected by an electrical or magnetic field. Beta particles, again, beta particles are essentially just electrons, so it has a charge of -1, as a small mass, just like we know electrons do. Electrons move faster than alpha particles. They're smaller, they move faster. It can ionize, but because it has a charge of only -1, it's not as strong an ionizer as an alpha particle. Penetrating, it's kind of middle of the road, so our beta particles are kind of our middle particles. Weak ionizer, weak penetration. But again, because it's a charged particle, it is impacted, it is affected by magnetic and electrical fields. Then our gamma radiation, our gamma rays, no mass because it's just electromagnetic energy. But again, because it's electromagnetic energy, it travels at the speed of light. It travels at the speed of electromagnetic radiation. Because it has no mass, no charge, it can't really ionize it. Unless it interacts directly with an electron, it's not going to ionize anything. So it's a very weak ionizer. But it has a lot of penetrating power. Because it has no mass, a lot of energy, it can penetrate a lot of materials. It gets stopped by something very dense like lead, but it can penetrate a lot of different materials. And again, because there's no charge, though, there's no deflection by a magnetic field or an electric field. So those are our three types of radiation, the primary properties of the three, and a little bit about them.